welcome to our Citizen Science, jointly put on by the Santa Cruz Children's Museum of Discovery in the Capitola Mall. I'm the director and founder of that, and would invite you all to come and visit from the crowd. We have Wednesday is Grandparents' Day, free.
Oh, cool.
And otherwise, we're open all the time, so come visit us. And with the Santa Cruz Public Library, we put these on monthly, the first Thursday of every month, 6:30 to 8. I'll just give you a little preview. Next month, we'll be doing sustainable living through zero waste. We'll be having a panel. We'll be sending out information about who's speaking, but it should be really interesting and interactive. So we're very excited to have all of you here. It's a wonderful crowd. Thank you. April will tell you more about herself. April Zilber and Martin Gaskell helping also. And we really appreciate you coming and sharing your skills and talents. So this should be fun.
Thank you.
Thank you.
I'm very excited to be here and talk about a project that I spent many months on, starting last fall. And I want to first of all thank the Public Library and the Children's, what do you call it again?
Children's Museum of Discovery.
Children's Museum of Discovery. Discovery is really important, you know, if you're going to explore a scientific or an artistic concept. So it's just in the right direction there. I want to thank Brenda McElroy for inviting me to give this talk. And I also want to express my undying gratitude to Martin Gaskell, who has mentored me throughout the project, and you will discover some of the ways in which his help was invaluable. Couldn't have done it without you. And there are a few other people who I may thank from time to time. One of them is sitting in the very back, Steve Cahill, an engineer friend who I had many technical discussions with. Thank you so much, Steve. Nick isn't here, is he? Okay. Oh well. So before I start actually talking about musical glass, the art and science of acoustics, I'd really like to take a quick audience poll. How many people here are engineers or work close to engineering, any kind of engineering? All right, look at that. Nice turnout. How many people are musicians or consider themselves musical? Yay, I see some crossover there. How many people are also, or instead, artists? I forgot to raise my hand on musical. That's wonderful. Okay, I bet there's some people who fit into some other category that I left out. Anyway, I just wanted to get a sense. There's a lot of different backgrounds in this room, and so I'm going to try and keep this kind of in the middle for everybody. If you have really intense technical questions, there's going to be time at the end to talk to Martin or me, or maybe even Steve will be willing to jump in on some of those questions. So the first thing is I should ask, what's the definition of acoustics? What do you think of when you hear the term acoustics? I shouldn't have put the definition. I gave you guys a little chance if you're speed readers. So, does anybody want to say something about what acoustics means?
Oh, I'm a layperson when it comes to that. Just, I think of how a room sounds, if it's reverberant or dead or something like that. I think of acoustics in that sense.
That's because Suzanne's a singer, and she really cares about how voice sounds in a space. Speaking of which, if I'm not loud enough, please tell me. Okay. There's another definition for acoustics, though, and that's the one that we're more concerned with tonight. And that is the branch of physics that deals with sound and sound waves. The other part of acoustics is what happens to the sound waves in the space. That's kind of important for us tonight, but it doesn't really directly impinge on my project. So, my original inspiration happened before I even moved to Santa Cruz County. I should say before I moved back. I went to college here. So when I was living in Berkeley after grad school, and I had become a glass artist instead of a scientist after all, I'm sitting at my kitchen table and there's this piece of my glass art hanging in the window. And I think I was practicing flute or practicing a song with my voice, I forget. And I was hearing resonance coming from that piece of glass art. And I'm like, well, that's cool. So then I started going ding, ding, you know, what's up with that? And I thought it was interesting, and I probably mentioned it to like one other glass artist friend, and then I dropped it. And I didn't think about it again for a really long time. But then it was, you know, sort of in the back of my mind. Last summer, not this one we just had, but the one in 2017, I was in Dune Art Open Studios, and Martin and his family, the Gaskells, came up to see my work. Martin, would you like to tell about your experience over there?
Sure. So Barbara does Dune art, and you should all do Dune art, by the way. And we looked up, and we knew that April had something on display. So Barbara went to told me where it was, so I went back later, and I went there because it was April. But here was this glass, and now I'm a scientist, but I'm also a composer and musician as well. And I look at this and I go, you know, it's beautiful glass, yes, but I look at this and I go, that's got modes of vibration to it. Mm-hmm. If I tap that gently, like, is it okay to tap this?
Yeah.
As I said to her there, so I went like this and tapped it gently. Oh, yes, a beautiful musical note. And so I sort of waxed openly about this to April, and I had just the perfect audience for this. It was like instant, oh yes, and we talked about half an hour, 45 minutes about this, all these plans and so on. So that's what led her astray.
I was like, how, Martin, help me figure this out. How do I make a series of fused glass panels that are tuned so that you can play music on them and it will sound good? How do I do that? It's got to be possible. So, it's because Martin supported my curiosity and my inspiration that we're all here today. All right, so sound is produced by vibration. If you strike something, you get a deflection, and you get compressions in the air. Expansion, compression, expansion, compression. It goes to your ear, and your eardrum does that thing. And it's going to depend on a few things. But where do I go from there? All right. The first thing, do you want to do the ruler demo now?
Sure, yeah.
Do the ruler demo now. This project had many different angles, all cooperating at once, so it was a little hard to organize.
Well, she's going to get into an equation somewhere.
Later on, an equation is coming.
I'm going to try and get them ready for the equation. Yeah. I get excited about equations. But if you want to understand how something vibrates, first of all, a real simple demonstration that sound is vibration. Here is a 12-inch wooden ruler. I'm just going to put it down on here, and I put it down somewhere towards the end. Can you all see that?
Mm-hmm. Yeah.
And I sort of prang the end there, so do it like that. I'll prang the end like that. Because you see it sort of vibrates up and down. You can all see that. Now, if I shorten the ruler a bit, it'll vibrate faster. Oh, you can hear that sound, isn't it? Bom, 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 and bom, 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 and so on, as you shorten it there. So it's vibrating up and down. So what should you say about this?
Well, what that tells me is that the longer it is, the lower the pitch.
Right.
The shorter it is, the higher the
Right.
pitch.
Now, so why is it vibrating? Well, it's because, if I hold it real tight here, if I apply force to it, like this, then it's going to pull back on it, and it's going to go flying like that, and it's going to accelerate and moving there. And how much it accelerates there is given by a very famous equation in physics, F equals ma, if you've had physics with that right. So force is mass times acceleration. The bigger the force, the more the acceleration, and the faster it will go in a given period of time. But there's another factor there, and that's the mass. This ruler has some mass to it, and we've dotted this ruler with a little extra mass to it here. So first of all, I'm going to put this down like this. I'm going to just prang it again. You hear the same sort of sound coming out. Let's just make it get 6 inches worth of ruler right there. There it is. Maybe 7 inches, like that. Right. So I'm going to prang. You should hear a note. Like that. And it's getting pretty fast. Now I'm going to turn it around. I'm going to put 7 inches on the other way. So I'm putting 7 inches, 7 inches, 7 inches. Okay, so 12 minus 5. So, but notice this time, same length of ruler, but we've added in this extra mass over here. And so this time when I do it, you can see it. If I make 9 inches, it's really obvious. Very obvious here. Well, if I did 9 inches around the other way, like that, we probably still more will like that. So the frequency it vibrates at, it depends on 3 things. It depends on how flexible the ruler is. Here's a very flexible ruler here. It's a very flexible one. This one will make it sound more, just go up and down really slowly like that. This one here is less flexible, so it gives a higher frequency. It depends on how flexible it is, how long the ruler is, and then how much mass there is involved there. So there's the factors involved. Is that what we should explain?
That's excellent.
Okay,
Yes.
okay.
Thank you so much. Okay, so when Martin and I had our conversation, he said what I needed to do was learn how to use some software. The software he recommended for me as a beginner was called Audacity. It's a free download. He said I could use this software to actually record the sound, get a frequency spectrum, analyze the frequency spectrum, find out what pitch all those notes, because you're going to get more than one sound out of these, not just a single tone. So I could use Audacity to analyze for a given size of plate what pitch it is. And then I could use Excel and do some math and create a way to calculate if I want a given frequency, how big does the glass piece have to be. So that was really, really exciting. So I will show you my very first experiment was to cut, this is all from the same exact manufacturer of window glass. They're all the same exact thickness.
How many are there? 3?
There's 3 here.
It's just a little hard to see because they're clear.
There, yeah, I know. I'll stand behind it. Can you see it better if I'm here?
Now that I know.
Yeah, there's a 12 by 12, there's a 10 by 10, and there's an 8 by 8. I just randomly chose those. I was pretty sure it wasn't going to have any significance in terms of musical notes or intervals, and it didn't really, but it's still fine for the experiment. All we care about is the frequency in hertz. We don't really care about A, B, C sharp. See, it doesn't sound that good as an instrument, but having that, maybe, yeah. Having that. Here's the 12 by 12 that I just played for you, the big one. This is a screenshot from Audacity. I've normalized and done a few other tweaks to the spectrum, but that's what the frequency waves look like. But that doesn't really tell me anything. I have to use the awesome power of Audacity to actually analyze it for me.
What, can you just say, is that time on
The x-axis is time.
Yeah, the x-axis is time,
So it
and then
decays?
this is amplitude.
Okay, so
Martin is going to jump in and correct me if I'm wrong, right?
Well, then perhaps I should sing it when it goes, doom, like that. It gets quiet as it goes from left to right.
That's true.
Yeah.
You are seeing, it's starting here and
Yeah.
you are seeing a decay.
Yeah.
Yeah. And we won't say more than that. There is more that could be said, but we won't because I'll never get through the talk if we stop constantly for those things. But here is that same 12 by 12 frequency spectrum, but now you can see where the peaks are. So this is analyzed to show me, you can see hertz going along the bottom, and then again, this is amplitude and decibels. And I had to write this down because of course you can't really tell from the graph, but this major peak here is at 303 hertz, and then I think this was 769, 817, and 969. Yeah, that looks about right, because it might be the other way around. Anyway, this was at
909 maybe.
303, 769, 817, 969 is what I wrote down. But at any rate, what's cool, and I can show you later if anybody cares, I won't show you right now, but what's cool about this is if I also did the spectra and the analysis for the other panels, and if I slid them across so that the major peaks would line up underneath each other, they do line up underneath each other. Okay, that means that there's something valid, that the rules of physics work with my glass. They should. But that was nice to know. So, okay, what did I do next? I had fun with Excel. Okay, so what I did, and I know it's teeny tiny, and I'm sorry, the screen's only so big, but way up at the top you see frequency, and I have 303 hertz, so I'm just looking at that big fundamental peak, the biggest first one, lowest one. And that's for the 12-inch long, so there's length in inches at the other side of the little table there. Then the 10-inch one was at 434, and the 8-inch one was at 681. So I'm going to show you an equation soon, very soon. But what we already knew was that the frequency is proportional, or I should say the other way around, the length is proportional to 1 over the square root of the frequency. So that's why I did some square root, 1 over the square root of hertz, and then I graphed 1 over the square root of hertz along the x-axis, and the length in inches going on the y-axis. And look how those square dots, those are the points, they fall on that straight line. They're really, really close. That's so wonderful. So then I could take y equals 209.1 and multiply to get a given length. So if I wanted A440, so I want 440 hertz, 1 over the square root of hertz is that, and then I multiply by 209.1, and I get 9.968 inches. Okay, I'm never going to be able to cut that exactly. We'll talk about that later. But 9.96, that's really close to 10 inches. The 10-inch one was at 434 hertz. 440 is just a little bit higher, so it should be just a little bit smaller than 10 inches, so it makes sense. Yay! Okay, so this was basically proof of concept. After this, I didn't have to play with plain old window glass. I could move on. And so the next thing I'm going to talk about is the equation. So my question was, and I asked many people this question, engineers, can I use math or physics to calculate the size frequency relationship instead of having to make examples, measure them, see where they fit, cut off bits, grind them, whatever. I mean, that's tedious. Can I be more precise if I use math? The answer is yes, but. So we know that frequency is dependent on the inverse square root of size, and it's also directly dependent on thickness. But there are some challenges. So here's where you get to see the equation. F frequency, and we're not giving a super detailed equation. This is the simple version. So that's a proportionality sign. It's proportional, not equal to, because we left out a few things. It's proportional to B, which is the thickness, L squared. L is the length, because we're in a square, it's L, not L and M. Or something. And then G, we're calling that the shear modulus. You can think of it as a constant that is about the stiffness of the material. So it's going to depend on the material. So that's a constant for a given material, for a given chemical composition of glass. And then rho, which is the density of the material. And again, that's going to depend on the chemical composition and so on. So that made me think, well, gee, I can control the variable L. I can control L. That's the length, the two sides of the square. I can't control the thickness as well, B, because glass comes in certain set thicknesses, and all I can do is pile them up. I could, but it would be super, super tedious, even more tedious than what I ended up having to do. I could grind flat like that, but that would be arduous, and the amount I would have to remove would be infinitesimal, and suddenly I would have removed too much, and oh my gosh, it's too late. So I'm better off with L because it can change a lot, but only have a small influence on F. Anyway, so, and I don't know these. I don't know the density. I don't know the shear modulus. I don't know the other constants that we didn't talk about. They haven't been measured for art glass. They've been measured for special kinds of glasses that are used for optics and astronomy and things like that. But so there's only so much data I have. So here was another problem. I mentioned that thickness is important. Well, guess what? Art glass isn't very consistent in thickness. So it turned out, I went back to my notebook, and I took so many notes. I was a scientist for this project, this part of the project. My clear glass sheets, just the clear glass ones, like the ones that are over there with the copper in them, they ranged from 0.105 to 0.119 inches. So that is a 6% variation on either side of the average in the middle. That's significant. Even an individual sheet could range from 1 to 5% along the sheet. So I'm like, well, this is really not going to be as reliable, and you'll see that. Whereas the window glass, when I measured the thickness with that, with calipers, it was less than 1% variation. So that's why those points were on a straight line so nicely. Okay, so this meant, you're welcome, thanks for coming. I was going to say, if you do need to leave, it's fine, I understand there is a back door, or you can walk quietly that way. I knew I was going to have to go ahead and use the empirical method, which is basically make some examples and then play them, record the spectra, and work from there. Do the same thing I showed you already with graphing in Excel. So I proceeded to finally get to the art part. Some of you are wondering, when is she going to get to the art part? All right. I will talk about how I chose these designs in a little while, but suffice it to say, often I use metal foils to make a design, an image, and then I sandwich the image between two layers of glass and I fuse it in my kiln. And so these are images that I've cut, and I'm going to use this and this together, and then I'm going to use this part in the middle with that little dot in the center for a different piece. So I take the figure in the ground, or you could say the negative and the positive, if you will. So I'm getting two pieces out of that, and I'm getting two pieces out of this. And then, see what I am here? I'm going to show you a short video. And in this video, you will see, if I can find the play button, there we go. This is my little test series.
Oh, love that.
Oh, I got to increase that volume. Actually, don't know how to do that. Ah, there we go. I'll play it one more time so you can really hear it.
Yeah.
This is the one thing I forgot to do on the pre-check. That should be loud enough. Hello. Nice. All right. So that was a good start, right? That was a good start. Not only did that give me a test series that I could analyze and then do some math with, but it also let me check a very important question, which is, do you think it will matter how much copper is sandwiched between the two layers of glass?
Yes.
So-
I
A
thought
little, a little.
But it didn't seem to have.
Exactly. You would think it would, right? This piece has a lot of copper foil. It's all the same thickness, but it has a lot of copper foil. This piece has only a little copper foil. I thought I might be in trouble here. I might have to tune everything for the design as well as the size. And OMG, how am I going to do that? But I was like, wow, I can do what I want. I'm so happy. So when I analyzed these in Audacity, they both had the dominant tone that you mostly heard just now at 514 hertz. And eventually I got to realizing that, you know, Audacity rounds to the nearest hertz. I wonder if they're a tiny bit different. So I used an app on my cell phone that does give you tenths of a hertz, and they're both 514.1.
Wow.
Amazing. So I cut them as carefully as I could to exactly the same size with the glass, and I used the same sheet of glass, so hopefully the thickness didn't vary too much. When you look at the higher harmonics, there are some little variations where one peak will be a couple hertz this way or 3 hertz that way, and I have a kind of an idea of why that might be, but I'm not going to talk about it right now. That's something you could ask me afterwards. But anyway, that just, so coming back to the art side of things, that was really important for you to know, that I can do the designs I want to do, and then what I get to do is talk about, okay, first I'm going to show you my calculations, just so you can see I did it again. There's the cobalt, that's going from the size of the smallest to the biggest, cobalt, amber, the pair of clears you see there, and then that flower one, and got a graph, and I have a straight line. I don't know if you can see from where you are, but the points are shifted a little bit. They're not perfect
Right.
on that line. So I knew that no matter what, I probably need to make my panels a tiny bit bigger than the math says, because we know that the frequency depends on the inverse square root of L, and so then I can do a little bit of grinding on 2 sides, so I keep it square, and that will allow me to fine tune. So I did a lot of that. But now I want to talk about, where did my design inspiration come from? Well, there's a reason why I decided to make square plates for this project. It's because there's a gentleman, his name is Ernst Cladding. Has anybody heard Cladding? Yes, okay, that's wonderful. And he did a lot of experiments with different sizes and shapes. He did triangles, squares, circles, you name it, where he would post it at the center, and then he would sprinkle sand on it, and then he would take a violin bow and vibrate the plate and get different patterns coming out. So he's the person, he wasn't the very first person to notice phenomena like this, but he was the first person to really work on it in a dedicated way for a long time. He also investigated meteorites, I believe it was. One of those Renaissance people, appropriately enough. And anyway, so he died in 1827. And then Mary Waller, who less people will have heard of, but she came along and she became a math-oriented physicist, and she started investigating his work and refining it and taking it further. Instead of using a violin bow, would anybody care to guess what she used to excite the vibration in her square plate?
Drumstick?
No.
Voice.
That's what we're going to do tonight, but no, actually, the escaping velocity of gas evaporating from dry ice.
Wow. Really?
Yeah, wow. Like, who would have thought of that? She did. I mean, I don't know how she thought of that. Maybe she picked up that tip from somebody else. I don't remember. So you see her here. I think it's a little hard to tell which hand is doing what. I think sometimes she held the dry ice underneath with a big glove on, and I think I kind of see a bulky glove. Every time I step on that, it gets dim. And then I think the hand on top might just be stabilizing one area on the plate. That's how she would control the waveform that she would get, because she's not and she could move the dry ice closer and further away from the underside of the plate, something like that. It's very complicated. I don't pretend to understand everything she understood, but she was really, really into symmetry. She was very driven by figuring all of that out, and there is a little image on your handout that comes from her work, Cladney's work and her work together, is what I would say. So now, that's where I was going to get the imagery, is from the square plates, from Cladney, what they call Cladding Patterns or Cladney figures on square plates. And we have a demo for you tonight, courtesy of the UCSC Physics Lab. They have loaned us frequency generator equipment with a square plate on top, and we have sand, and Martin is going to, and you're welcome to like all get up and walk over there, and if the sound gets obnoxious, just plug your ears.
Oh, this is so cool.
Okay, so you gather around here. As close as you can. This is not dry ice, this is sand. This is a black plate here. So what I've got here from UCSC is it's an oscillator, and it makes a sound. And this thing here is like the coil of a loudspeaker. There's a metal plate on top of it here, and I've got two controls here. One I can set a frequency on, and the other one here I just turn the volume. So I'm going to set so I've got a crib sheet here, so I can turn the frequency down to 68 hertz. That's a sort of slightly higher pitch than the hum you get from a loudspeaker or mains or something. So 68 hertz is about there, not very precise here. There we go, somewhere around there. And now I'm going to turn up the volume. And if you're nearby, you can just hear that. But
Oh, look.
come closer, you're not too far.
Wow.
Let's have short people sit on the front. Short people go on the front here, and then up here on the back. And I'm going to have a bottle, so the closer you get, the closer. So I'll do it again. So I start off with the sand, sort of spread somewhere over here. Just pretty randomly arrange my pattern like that. And then I'm going to make it, I turn up the voltage here, make it vibrate.
Yep.
Wow.
That's beautiful. Oh, it's making that symmetric pattern.
Well, it's a matter of how the plate bends here. We have to drive. This is different from April's plates. April's plates are free hanging. She's going to talk about that. With corners. This is held on a post in the middle here. So the post in the middle is going to vibrate up and down. But if I take this piece of paper here and I push it up and down, we see the paper bends like that. Is one of the ways that it can bend. And if I do that, well, there's some parts that don't bend, and the parts that don't bend are where the sand will stay put. So the sand is staying put in the parts that are not bending. In the middle, the sand should run away from it. The edges are going up and flapping up and down, but somewhere in between, the name we get to that are called the nodal lines, the bits that don't move. So I'm going to start on again. I'm going to be quite loud, and it's still not very much on those nodal lines. Let's turn that one down, and I'm going to go my crib sheet. So that's the lowest resonant frequency, and I'm going to go up to
Degeneracy.
up to what? Yeah, that was actually interesting. It could have vibrated the other direction. It could have gone like this. Unless since you asked about that, let's see if we can do that.
A little bit different frequency, maybe.
Yeah, no, I don't think so. Well, very slightly, but that could be. Let's see what we can do about that. I'm also wondering if we touch the plate, could we do that? So suppose I touch the plate there and there. Maybe I can do it. Go the other direction.
Yeah. Yeah.
Oh, wow.
Yeah.
Now let go.
Let's just shoot the frequency. We've got a lower frequency, higher frequency. The thing about that plate really likes to go that direction.
It's not symmetrical.
It's not very symmetrical. Yeah. If we'd done extensive experiments beforehand, we could have found the frequencies we made the plate go around the other way. But anyhow, here's another pattern which is going to be symmetric. So I'm going to go up to 80 hertz here. Hertz means cycles per second. So sprinkle the sand around here. Just get in the box to keep it all. Raise that. Something like that. And put some sand on the floor here.
Nice.
This is a higher frequency. Going through two inches. I lose all my sand. What I was trying to do, what was supposed to make a square pattern.
Started to.
It did, yes. I got too carried away.
Wow.
With the first one, when I went more vigorously, it sort of sharpened the pattern. This one here is not quite so stable. But we're seeing a sort of squarish pattern.
Are the wires touching it?
Actually, the wires slightly touching. That should not be touching.
We tried not to have the wires touch.
Try that.
There's
That
more
might
tape.
be a small factor. But again, it's not quite sufficient. That's nice. There we go. Yeah. Right. So let's go up to 176 hertz now. 40, 50, 60, 70. There it is, 176 hertz. Do our thing with the sand again over here. Sand on there. And this is going to be a high pitch sound again. That's going to be an octave higher than the previous one we had. It's going to be a rather complicated pattern. It's going to be a little square in the middle and little corner bits over there.
So how's
Right. So
the plate doing?
so you can bend it like this. You also bend it like that, and you can bend it like that. And there are many ways you can fold it and bend it if you think about it. They're constrained by the number of nodes and things. The math that described is actually quite complicated. So that was that one. Let's go up again. Now I'm going to go up to 250 hertz. That's about middle C. You'll see that this existing pattern is going to dissolve. I'm going to get to 250 hertz. That's like being a B and a C. Middle C, middle B. It's also the frequency of my electric toothbrush too. For my birthday, I was given an electric toothbrush. So of course, the thing I had to go was find what the frequency really was.
We would, wouldn't we?
Doorbell.
Now, the pattern is going to change. And we have a sort of elaborate pattern here. It's changing.
Wow.
Something different there. I can try it at 382 hertz. It looks like a rather pretty picture, but based on my crib sheet here, so going up to 382. So this is going to start getting more obnoxious now. Because it's too loud, so your fingers in your ears. Up to 382 hertz is what the crib sheet says. Around there.
Can you shift that over a little bit so it doesn't touch for sure? Because I think you're getting something similar.
You might need more tape.
No, it's not. This is not
They're not
touching it.
touching.
No, it's well clear. Well clear with it. So let's move this around. Like that.
Maybe more sand on the one side.
Not really. Well, the hole might not be exactly in the middle either. First to drill the hole might not realize how critical it is to get the hole exactly in the middle. Right, so this is going to be louder and higher. Maybe two.
This is only a test.
That's right. This should produce a sort of crisscross pattern.
Yeah, right, yeah.
Residential text.
hertz. Now I'm going to try another one now. There's like a 477.
And Martin, maybe that has to be the left.
Oh, that's one. That's one. Too much fun here. This is the last one. 477. Smooth it
Well, I've got
around.
to be audience play time too.
Right.
Not with that, but.
Right. Okay. Here we go again.
Beautiful.
Wow.
That's April.
Looks like
That's April.
Yes,
That's
Ah.
here.
Very good.
Wow.
That's beautiful.
Wow, and how many hertz was that?
There we are.
What was that, Martin? 400?
That is 477 hertz.
So before you get too excited about what hertz goes with the pattern, keep in mind the frequency depends on the thickness and the size of the plate. Every square plate that is center constrained, like that one is with that post, is going to exhibit all the same modes, but not at the same frequencies, because they have different thickness and size.
So after it was finished, you can come on your own and play around with these.
Except for that, Martin, then I want you to supervise that.
I mean, afterwards, yes.
If we do that, Martin, I would want you to supervise it so people don't have the volume turned up while they're. So that was a great demonstration. And you can find on your handout that there's this person whose YouTube channel is called Respup. And he has put Cladding videos on there. The link that I gave you is for ones where you can hear the frequency and you have to keep turning your volume down on your sound system so that it doesn't hurt your ears. He also has one where he just edited it so that it had all the patterns he liked. You see them changing and there's some background music that sounds lovely but has nothing to do with the frequency producing the pattern. So that's this resonance experiment full version with tones, the one you need to watch your hearing with. There's another version, like I say, that's shorter and edited and you don't have to worry about your hearing because it's just got music. And if you do Cladding video, you'll find lots of other things.
Okay.
Yes?
What if the glass wasn't pure? If there were some impurities or bubbles or whatever?
Well, so that was a metal plate, but yeah, if it hadn't been a uniform plate, it would introduce anomalies into, especially if there was a surface variation. Yeah, or like an area where it was thinner or thicker, that would introduce variations in the nodal patterns that you see. And it might shift the frequency at which a particular pattern appeared as well. That's an insightful question.
So the illustrations here show a node going through the center of the plate, which is unlike the demo here,
I know.
where the center is actually being driven.
I am going to say that this is a very complex figure. Martin and I tried to see if we could quickly figure out a way to explain it easily, and it's not quick, so I'm not going to talk about it right now, about these figures. It's from Chladni's work, but also from A Study in Symmetry by Mary Waller, who I mentioned had taken his work up to another level, and it's very difficult to understand. It's not something I can explain in 2 minutes, unfortunately. But maybe we can talk a little bit about it after my this much understanding of it so far. So, okay, that was an excellent demo. Now, going back to art. Okay, I've chosen that I'm going to use Chladni figures. You've seen some examples. But what color glass should I use? I'm going to use copper. What color glass should I use? Has anybody heard of, let's see, was it Scriabin? Scriabin, thank you for correcting my pronunciation. He had synesthesia. So I thought, oh, that would be really cool. Let me look at his color, musical note relationship thing. He has like this whole, theory that worked for him. I looked at it and it's beautiful, but and I didn't put a slide on for you, but you can look this up if you're interested. What I found is that from half step to the next half step to the next half step, the hue shifted by a fraction. It was a really subtle shift from note to note. Well, that clearly wouldn't work for me because the art glass I have access to doesn't have such fine gradations in hue. And so that would needlessly complicate my project. So I had a different idea. And my idea was, okay, well, I also had a few other things I had to decide. Like, what would be a good key? Should I, you know, what do I choose? I'm going to make an octave. I decided I'm going to make an octave. I'm not going, this is my first blast musical instrument. I'm not going to make a chromatic scale that has 12 half steps in it. I'm going to make a diatonic scale that has, you know, whole step, half step, and so on. So who did I consult? I consulted a singer that some of you know by the name of Jace, because I have a woman's singing voice, so I know what notes I can sing, but I didn't really have a good understanding of what notes male voices can sing, or just lower voices in general. And so I talked to this pretty good singer about this issue, and we came up with the idea that A, from A220 to A440, would be a good range that all voices could sing to. Why did I care about that? Because, remember, my very first inspiration was I was like singing or playing next to a panel, and I thought it'd be so cool for people to be able to do that, to hear the resonance coming back, and you will get a chance to do that tonight. So, okay, so that's how I chose my key. How I chose my colors was I thought, let me make it easy for people. It's going to be A major, there's going to be the tonic note and the octave. Those can both be cobalt. The other common intervals that we're used to hearing in Western music in a chord are the third and the fifth. Let me make those be cobalt also. Let all the rest be clear. Really simple. So that's what I did. And the next thing I'm going to show, okay, so I mentioned I would have to fine tune. I had to take every plate, measure its sound spectrum in Audacity, and then if it wasn't quite right, I had to grind it. And I used a lapping wheel, and this is in the cold working studio of Christy Aloisi and Scott Graham in Boulder Creek. They have a little store of viscosity glass. They've been very good to me in this project. I used their equipment for hours and hours and hours. So, I mean, I think maybe I might have had an 8-hour day there one time, and I had to go back a lot of times because some of my plates came out really close to right on, and some of them came out way too low. And when I mean way too low, I mean I had to grind off like a 1/4 inch on 2 sides. That's a lot of material to remove. So it's tedious. You grind, and then you grind the other side the same amount, and then you dry it off, and you hang it up, and you record with your handy laptop, and check, am I there yet? No, I'm not there yet. Yes?
You did this after they were fused?
Yes, after they were fused.
Did
So
anything change when they fused, during, before and after? Did anything?
well, you see, I have 2 layers of glass with metal in between, so they're not fused yet, so you can't test.
You couldn't test it?
You can't test it
Oh,
until you fuse
can
it.
tell.
Yeah, once you've fused it, then you can start testing it. So I just wanted to show, you know, safety equipment. I had hearing protection, eye protection, inhalation of, it would be a mist that had silica dust in it. So I probably could have been wearing a respirator, a full-on respirator instead of a mask, but because there is water holding the dust, and because I did it for so many hours, that would have been really hard to wear a full-on respirator the whole time. But so that's the A220. That's the bottom of the octave. And I also had to build a stand for it.
Wonderful.
So Nick isn't here tonight, but he let me work in his machine shop, and he helped me figure out how to build this copper stand. Steve helped me install the darn thing at Filoli Gardens this summer. This was on display for 3 months. It had to be very sturdy. It had to not sag, so we put dowels inside those crossbars. Figured out cord to hang it with, figured out what to use as a mallet to strike them with. And I also want to acknowledge Filoli. Not only was this huge project dependent on having a mentor like Martin to help me figure out some of the tricky bits, but I needed to know that there was a reason to put so much time and resources into it. And the reason was that I had a place for it to live all summer for people to go and see it and play it. And it was really well received. And kids loved it, but so did percussionists. So I'm going to unveil the instrument and let people play, and please use the rubber-tipped end of the stick, and please come and ask me and Martin questions. If you want to play with the Cladding generator, you should have supervision by somebody who knows how to protect your hearing, just so you don't accidentally blow us out. And here's my thank you slide to Martin, to Steve, to Christy and Scott. Not only did they let me use their cold working equipment, but they also got me invited to be in the Filoli summer sculpture. So they were crucial for that. Nick, as I said, helped me build the stand. Evan Piers, I've had conversations with. He's another engineer who's very interested in acoustics. Filoli Gardens is on there. And everybody who let me bend their ear, colleagues of mine in both library systems, particularly Brenda and Ken. Some people actually helped me look stuff up. Thank you all so much. So one last word I want to say is that the meta level of this project, aren't you smart? Thank you, Julie. The meta level of this whole project is not even about the art and the science. It's about the fact that if you have something that really inspires you, and you get excited every time you talk to somebody else about it, do it. Do it. You've got what you need to see yourself through. And the other side of that is, if you're listening to somebody who's that excited about something, and you have just that little bit of advice you can offer, it might be a website, it might be, hey, I know somebody who's tried something like that. It might be, I can show you how to do that math. I can teach you Audacity. I'll help you build that stand. It makes such a huge difference. A ripple effect. All right, here is the instrument. Because I want you all to have time to play any of the glass that you would like to play and ask questions. But here's the A220. C sharp. Sounding a little damped. Gives you the chords, so here's the third. And then here's the fifth. And here's the octave. Now, because they are bell plates and they have other frequency, other resonances happening, they're not like a pure note like a flute or a recorder would be. So you're going to hear some funny interferences. So playing the music slowly is one way to handle that. Another way to handle it is to not use as hard of a rubber stick. There are some softer balls, and play it more percussionist style, which is not the way I know how to play, but other people might know how to do that. So please have at it. And thank you so much, everybody, for coming.
That one is a little long.
There's a big bend in there.
Okay. Great.
This is love.
Oh, wow.
Thank you.